This is the Chem 1 lecture for acid-base titrations. So today we're going to be reacting acids with bases. We're going to have two solutions that we're going to be mixing together. And so we first have to remember what happens when we mix or react an acid with a base. If you remember back from Unit 10, it was called a double replacement reaction, and we called out something called a neutralization reaction. When an acid and a base react, it will always produce salt and water. Remembering that a salt is just an ionic compound with a positive and negative charge. And so if we look at the pH scale, when we react an acid and a base, instead of exploding or reacting, it actually just moves towards the middle, which is neutral on the pH scale. Hence, we have water. In this example, we have sulfuric acid reacts with potassium hydroxide. What would we produce? So double replacement, we swap the two cations and we'd produce potassium sulfate, and HOH is water. And then balancing is going to be important because mole ratios are going to be back today. The mole never goes away. So we need 2 potassium hydroxides and 2 moles of water. Okay, so what can we expect about the pH when there are equal amounts of hydrogen and hydroxide ions? You would expect your pH to be 7 because you are neutral. There are equal amounts of hydrogen and hydroxide. If you have an excess of hydrogens, you know this solution is acidic, so we would expect the pH to be less than 7. All right, so 1, 2, 3, 4, 5, 6, 6.9. And if you have excess hydroxide, we would expect our pH to be greater than 7. So we are borrowing the Arrhenius theory, talking about dissociating hydrogens and hydroxides. So today is going to be about trying to find that neutral point. And so in order to neutralize an acid-base reaction, what do you think has to take place? You have to react your two solutions until there's an equal amount of hydrogen and hydroxide ions. Well, how are you going to know when things are neutral? Great question. You're going to have to bring in something called an indicator. And so an indicator indicates if something is acidic or basic. So in this picture over here, when it's acidic, the solution is blue. When it's basic, the solution is red. And so when you're at neutral is right when you would be switching colors. So there are a lot of different indicators. A common one that we typically use in lab is called phenolphthalein, which is colorless when it is acidic, and pink when it's basic. So if you're using the indicator phenolphthalein, that neutral point, or we're going to call it equivalence point, you're looking for right when it's about to switch from clear to pink or pink to clear. So the official setup of a titration is pictured here on the left. You typically have a standard ring stand, a glass burette, and an Erlenmeyer flask, and you put an indicator in there, and you place, you're going to have always two solutions. One is acidic, one is basic, right? Today's lesson is called acid-base titrations. And you're going to have one of the solutions in the Erlenmeyer flask, typically your unknown solution, and then one of the solutions in your burette, and then you're going to drip, or fancy word, you're going to titrate until you reach that equivalence point. So until you get to that right when it starts to color change. And the reason titration is a helpful technique is because when we've reached the equivalence point, or that neutral point, we now know some information. We know that there are equal amounts of hydrogen ions and hydroxide because we've gotten to neutral where there's an equal amount of hydrogens and hydroxides. So typically in a titration situation, your known is something you know the molarity of and you know the volume of. And then your unknown, you either have the molarity or the volume, but you don't have both. And so it's the process of allowing you to find an unknown value, because once we know how many moles there are, let's say, of the acid, you can now figure out how many moles there are of the base, assuming you've reached the equivalence point. Now, today's lesson would be really easy if we gave you guys always just one-to-one acids and bases. meaning when hydrochloric acid breaks up, it breaks up into one single hydrogen. When sodium hydroxide breaks up, it breaks into one single hydroxide. So at the equivalence point, if I have 1 mole of hydroxide, I would have 1 mole of hydrogen. However, we're going to give you guys times where the acid or the base is not a 1-to-1 ratio. And so we're going to have to bring back stoichiometry and account for example, if I have sulfuric acid, well, when it breaks up, let's say I have 1 mole of sulfuric acid, well, it's going to dissociate 2 hydrogens. So if I had 1 mole, I now have 2 moles of my hydrogen ions. So long story short, we're going to give you a step-by-step process to work through a titration problem. Okay, so example number 1. In a titration, 21.4 milliliters of 0.0154 molar solution of barium hydroxide are added to 20 milliliters of hydrochloric acid. They want to know the molarity of the hydrochloric acid. So our first recommendation, or step 1, is always balance your acid-base reaction. So I'm going to need a 2 in front of the hydrochloric acid and a 2 in front of water. Then we recommend placing all of the given information under each substance of the balanced equation. So the 21.4 milliliters, I would put, not paying attention, it says molarity. So barium hydroxide, the molarity is 0.0154 molar. The volume it took to titrate or to reach neutral was 21.4 milliliters. The volume of HCl is 20 milliliters, and we're looking for the molarity of HCl. So then, pretty obviously, our unknown is the hydrochloric acid, because we do not know the molarity, and our known is the barium hydroxide. So step 1 and 2 are good steps, but really the next 3 steps is when I think of titration, I think of steps 3, 4, 5, is calculate the moles of the known, calculate the moles of the unknown, and then use your molarity formula to figure out your missing piece. So we want to calculate the moles of our known, and we're going to do that by using our molarity formula. So from our known information, we can sub in our molarity being 0.0154 and our volume. And then just be really careful, 21.4 milliliters is not the same thing as liters, so I would have to convert milliliters to liters by dividing by 1,000 or moving your decimal place 3 spots to the left, and I get 0.0214 liters. I can cross multiply and get my moles of my known, which once again is the base barium hydroxide. And that equals a very tiny number, 3.3 times 10 to the negative 4th moles of barium hydroxide. So the fact that I'm back in the formula barium hydroxide, I'm not saying how many hydroxides are there, but I'm saying how many moles I have. And so we're at the equivalence point where H's equal OH's. But as I mentioned earlier, because we are dealing with not 1-to-1 acids and bases, we are having to account for the hydrogen and hydroxide ratio. So step 4, we want to calculate the moles of the unknown. And because we're at the equivalence point, we can start with our moles of known, and then we just have to use stoichiometry for our mole ratio. So barium hydroxide, the ratio is a 1. So for every 1 mole of barium hydroxide, there are going to be needed 2 moles of hydrochloric acid to make sure that they are equivalent to each other. So 3.3 times 10 to the negative 4th times 2 gives me 6.6 times 10 to the negative 4th moles of hydrochloric acid. So I just switched from being in the base and now I'm in the acid. And so our final step is, now that we know the moles of the unknown and we also have the volume of the unknown, we can use the molarity formula again, but this time subbing in things for our unknown. So we know our moles are 6.6 times 10 to the negative fourth, and we know our volume of our unknown was 20 milliliters. And we know that our molarity formula requires liters, so it's 0.020 liters. And I'll divide 6.6 e negative 4 divided by 0.02, and the molarity of our, I'll say unknown acid, but we know the acid's hydrochloric acid. But our unknown molarity is 0.033 molar of hydrochloric acid. So the main three steps is you solve for the moles of your known, find the moles of your unknown, and then plug it back into molarity. All right, let's try another example. And so the way we just did the titration is probably what is most common. We're usually solving for the molarity, but they could throw a problem where like your unknown is how much volume is it going to take to neutralize it. So let's jump in. So it says, what volume of a 0.35 molar sodium hydroxide solution would have to be added to 15 milliliters of a 0.75 molar solution? So step one, I want to balance the equation. We're putting a 2 in front of sodium hydroxide and a 2 in front of water. And then it says label, meaning label the known and the unknown. So what volume of sodium hydroxide? So that is going to be my unknown. And then I'm going to write everything down for sulfuric acid. It took 15 mils of 0.75. All right, so then we get into the meat of it. We want to first calculate the moles of our known, which I forgot to label, is sulfuric acid, because we know the volume and the molarity. So plugging our knowns into the molarity formula, we've got 0.75 molar on the left. 15 mils we need to convert to liters, which y'all don't have to show me that work. And then we need to solve for moles. So you can cross multiply or multiply each side by 0.015, whichever your style is. And we get the moles of our known as 0.011. I'm going to round up to 3 moles of sulfuric acid. So we know that many moles are at the equivalence point of our acid. And so then we are going to now solve for the moles of our unknown, which is the base in this example. And to do that, we are going to start with the moles of our known, 0.0113 sulfuric acid. And we are going to use our mole ratio to make sure our moles are proportional to each other. So looking at our balanced equation, sulfuric acid has a mole ratio of 1. So for every 1 mole of sulfuric acid, there are 2 moles of sodium hydroxide needed so that they are equivalent. So 0.0113 times 2 gives us 0.0226 moles of our base. And so now that we have the moles of our unknown, we can go back into the molarity formula, this time subbing in everything for our unknown. So we know the moles of our unknown is 0.0226. And then I'm going to look back to my notes. Our unknown, we have the molarity this time, and we're looking for the volume. So we know the big M, the left side, is 0.35 molar. And we're looking for that volume. So I put something over 1, so I have fraction equals a fraction, so I can cross multiply and divide. So 0.0226 times 1 is the same number, divided by 0.35 will give us our volume in liters, which comes out to be 0.0646 liters, or if you wanted to convert back into milliliters, multiplying it by 1,000, you'd have 64.6 milliliters. So this would be the volume needed to reach the equivalence point. All right, so now it is your turn to practice, and we've taken away the scaffolding. Now you have your notes, and we wrote the steps above, but we have 3 practice problems for you to try out. Good luck.